Thanks for the introduction. Sorry for the delay. I'm actually a PhD student at UBC with Wolfgang Heidrich, and this work was completed when I was a visiting researcher at Ramesh's lab last year. Schlieren photography is a non-intrusive optical imaging technique for dynamically changing refractive index fields. So these techniques optically encode otherwise invisible transparent refraction into observable changes in intensity and color. All these images are taken by Gary Settles and his group, who was a major inspiration for all of this work. And these techniques allow the visualization of transparent flows in gases, fluids, also the refraction caused by transparent solids, and also shock waves. Applications for Schlieren photography include aeronautical design, ballistics, and also more recently computer graphics and vision applications. So on the left-hand side you see blunt body entrance vehicles that re-enter the orbit from space, and also a wing, both of these as small models in a wind tunnel at hypersonic speeds. So you can actually see the shock waves that are forming around these vehicles, which allows the study of how to design these objects in the best possible way. On the upper right, you see a rifle being fired and the shock wave that is created by this rifle and the bullet coming out in the front. The lower right just shows some reconstructed gases that is actually just hot air which disturbs the refractive index, and that can be used for rendering, for instance. Although some of these applications have more recently been partially replaced by computational fluid dynamics, Schlieren photography remains an important tool for many different applications. And although recent developments have made some of these setups somewhat more practical, generally the optical setups required for traditional Schlieren photography are pretty big, and therefore constrain these setups to laboratory environments. Furthermore, expensive or very well precisely calibrated optical elements are required, which makes the setup somewhat expensive as well. We present a new and portable approach to Schlieren photography that uses light field probes, which are basically placed behind a transparent object of interest and then just photographed with a camera. Our current implementation of these probes are simple lenslet arrays, of which you can see an illustration of a cutaway view here. So on the left you see the lenslets, and on the right the frequency pattern, the high frequency pattern that's underneath the lenslets. So when you observe such a probe from straight on without any refractive medium in the optical path, it looks almost white, whereas a refractive object would optically encode the angle and magnitude of the refraction in changes of color and intensity. Our main contributions are the introduction of high-dimensional probes for computational imaging, and we also introduce a new type of background-oriented Schlieren imaging approach, which we call light field background-oriented Schlieren, or short LFBOS. So here's an example. On the left you basically see a glass unicorn in front of a uniform light source. It's almost transparent. And on the right you see it in front of a probe. So this probe looks almost white when you just look at it without the refraction, and the angles and magnitudes of the refraction caused by the glass unicorn are directly encoded in color tone and saturation, respectively. But let's take a step back and look at how traditional Schlieren works. So a typical setup consists of two lenses with a refractive medium in between, as well as an optical filter, which in this case is a knife edge. The scene is observed by a standard camera. A point light source illuminates the scene, and on the bottom row you see light fields as it progresses through the optical setup. We use a space and angle representation. You've seen this many times so far. So the point light source has no spatial extent and emits light uniformly in all different directions. The first lens simply collimates this point light source, and all the light rays that get transported through this space in between the two lenses remain parallel, whereas rays that get refracted get bent upwards or downwards, right? The second lens then focuses all these light rays on the plane with the optical filter, and all the unchanged parallel rays are basically focused right in the center of that plane. All the light rays that are bend downwards in this 1D schematic basically are filtered out by the knife edge filter because they get bent down by the lens, whereas all the light rays that get refracted upwards can reach the sensor and in that way optically encode changes in the refractive index in the intensity distribution on the sensor. Simultaneously, each pixel on the sensor is focused on the refractive medium itself, which allows us to actually take a photograph of the scene or of the refractive medium along with the intensity encoded refraction. The advantages of traditional Schlieren optics or Schlieren photography are that you get a very high angular resolution and that all the processing is done optically. So in this case, no computation is actually necessary. The disadvantages are that normally relatively expensive hardware is being used and normally these configurations are constrained to laboratory environments because they are rather bulky. The encoded information in this optical system is only two-dimensional because what you encode is the angular deflection. With the upcoming of more computational processing power, background-oriented Schlieren methods have been invented. So these work by taking a picture of a high-frequency background, such as this noisy image on the left, which has no distortion in the scene. And on the right, you basically see the same scene with very slight distortions. They're so slight you can't actually see them on this slide, but when you run an optical flow algorithm on these two images, you can basically compute the optical flow vectors between the two images. And then you can subsequently color code them, for instance, using the filters that have been known in traditional Schlieren for a while, by coding the magnitudes and angles, for instance. The advantages of background-oriented Schlieren is that the setups are very easy. You just print a high-frequency pattern and put it in the scene. You get a very high spatial resolution, and the setups are very inexpensive. The disadvantages are that the optical flow can be computationally very expensive, especially for high resolutions. The form factor can get quite large if the distortions are very slight, because you have to place the background at a significant distance to the object so that the distortions are actually observable by the camera. Again, the encoded information is only 2D, as only the spatial displacement on the background pattern is observed. With our probes, we can basically encode the position and the angle on the probe surface, and thereby design a light field illumination that is transported to the refractive medium, disturbed by that optical medium, which you can see here in some contour lines in the light field, then filtered by a pinhole or a very small aperture of a camera, and depending on the light field that is being encoded on the probe, can achieve the same effects as very complicated traditional Schlieren setups. The advantages of these light field probes are that the encoded information is up to 4-dimensional, because you can encode the space and the angle on the probe. The setups are quite easy and inexpensive, because all we need is printed transparency and a lenslet array with a light box, for instance, for the background. The form factor is small. All the processing at this stage of the algorithm is done optically. The major disadvantage at this time is the fixed spatial angular resolution trade-off imposed by the lenslet arrays. So here's a photo of some of our setups. It may look a little confusing on the left, but what you see is a fanned-out view of the probe. You see a light box in the background that provides uniform background orientation, illumination, and then a printed transparency that we just print with an inkjet printer on top of that, followed by a lenslet array that just sits on top of the transparency. In the magnification, you see this high-frequency pattern of the transparency on the left, and the lenslet array sitting on top of it on the right. And just because they're both high frequency, they create moire patterns, which you see in the picture, hopefully. On the right, we see a typical setup with the probe behind a refractive object and a camera observing that from the front. Let me also talk a little bit about how we design the patterns of the transparencies in order to create a light field that illuminates the scene. So for purely angular codes, you basically assign a color for each pixel that is similar under each lenslet. So this way you can encode different directions of the probe with different colors, for instance, with a color gradient. Encoding the spatial position on the probe requires you to color the entire lenslet with the same color, but changing the color over different lenslets. So this way you can code space and angle of a lenslet-based probe. The design criteria for the light fields that we've identified for this applications are: one, the color or intensity distribution should be smooth in the 4D space so that we can calibrate or basically account for slight miscalibrations in the actual manufacturing process. Ideally, the color distribution should be independent of any absorption that's going on in the transparent medium. If that's negligible, we don't have to worry about it, but this could be done by using only hue and saturation, for instance. Also, we need to consider if the light field probe serves as an absolute reference frame, or if the light field is actually pre-warped in the probe in order to account for a static camera at some finite position. The image formation process is governed by the Ray equation of geometric optics that you see in equation 1 here. And I don't want to go too much into detail, but I just want to give you some details. This has been shown to be able to decouple into a coupled system of first-order ODEs. And if you look at the right part of equation 2, you can basically see that the local change in ray direction is directly related to the refractive index gradient. So in a homogeneous medium where the gradient is 0, light rays just travel in a straight ray. That's all it says. So looking at a medium with larger extent, the global light deflection from an incoming ray to an outgoing ray is just the integral over all the local changes of ray direction, or along the path of propagation, or similarly the integral over the refractive index field at this place along the path. The camera image is then basically just a lookup table in the background light field that takes the light ray of a pixel, and propagates it through the medium with the angle, and also accounting for some global displacement. So here are some examples. This is just a probe, which looks gray because there's no refractive object in the optical path. This is a convex lens that's almost invisible because it's shown in front of a uniform illumination source. There's some absorption going on, but it's almost negligible. This is the same lens placed in front of the probe. So you can see that the vertical gradient of the refractive index field, which is basically the shape of the surface, is being revealed. And the same happens if we just turn the probe around. So this particular probe is just a lenticular array which consists of one-dimensional semi-cylindrical lenticular. And the code or the intensity code underneath the lenticulars is a one-dimensional intensity gradient, which is the same under each lenticular in this case. So you can see this in these cutaway illustrations. They may be a little bit confusing, but I hope you get the idea. This is a more complex object placed in front of a uniform light source and placed in front of the probe. So you can see the structure in the center of the plate appearing, which is again the horizontal and the vertical gradient of the refractive index field, and you can also see that in the magnifications on top. And we can just crop an intensity gradient from a part of the probe that is not covered by lenticulars, and use that as a color bar, and together with the fixed field of view of the lenslet arrays, we can assign numbers to the actual colors. So we can actually take quantitative measurements rather than just pretty pictures. And we can also encode a variety of different angular filters in these kinds of probes. So in this case, we see an annular bright field and an annular dark field, which is inspired by filters used in microscopy. And at this point, I would like to point you to Mark Levoy's excellent work on light field illumination for microscopy. So the annular bright field basically leaves all the light rays untouched that are not refracted or that only are slightly refracted, whereas rays that get strongly refracted at the outside of the object get completely cancelled out in this case. The annular dark field is the exact inverse, so all the light rays that undergo no or just minor refraction are cancelled out, and only light rays that observe significant refraction are actually highlighted. We experimented with a wide variety of different angular filters, for instance, circular intensity gradients and hard horizontal and vertical cutoffs. This just shows a variety of filters that you can use. And so here we used a filter that is traditionally used in Schlieren photography, which is called rainbow Schlieren. So underneath each lenslet, and this time we have a hexagonal lenslet array again, we have the hue and saturation color wheel underneath each lenslet. It's the same under each lenslet. So if you place a convex lens in front of this probe, you can nicely see how it encodes the refraction, because the angle of refraction is coded in the color tone and the magnitude in the saturation. So you've seen the same filter earlier for the unicorn in the very beginning. Here are just a few more objects in front of the same probe. And we can not only code the refraction caused by transparent solids, but also those imposed by fluids. So in this case, you see a clear water bottle that's filled with cornstarch and water on top of that. And we did some messy experiments with these and injected water into the cornstarch, and you can nicely see that the complex interaction between these fluids is encoded in these colors, which is quite nice. Here's a less dramatic experiment where you again see a bottle with cornstarch and air bubbles rising in that. You can see some of the refraction going on inside the bottle and in the air bubbles as well. And this is just a video, a high-speed video that I shot with a consumer camera, so the image quality isn't very good, but you get the idea. Again, water is being injected into the cornstarch. It's actually quite amazing what you can do with consumer cameras nowadays. All right. So far, we've only seen angular filters, but the probes actually enable us to use spatial angular filters as well. So here's a refractive object, which is just a small bowl, a glass bowl under room illumination and in front of the probe. So this probe has a color coding scheme that's seen on the right. So the red and blue color channels encode the horizontal and vertical direction on the probe by having repetitive patterns underneath each lenslet. And the green color channel basically encodes the spatial position on the probe. That's why the green channel becomes brighter as you go down. From the camera image, we can then extract the vertical position of each refracted ray on the background plane, as well as the vertical and horizontal gradients. And obviously, one of the applications that for this technique is to reconstruct refractive surfaces that are actually transparent. We actually didn't get nice results before the paper deadline, but I'll show you some preliminary results that we got now. So this geometry shape is just reconstructed from the extracted gradients. And since this is a single image technique, we can also do that for dynamic media, such as a water drop being injected into a water surface here. So on the upper left, you see the camera images. On the lower left, the extracted gradients, and then this can be integrated to get the surface, which can subsequently be used for rendering. But again, these are preliminary results that aren't actually in the paper. Coming back to background-oriented Schlieren, I mentioned before that these compare two different images, one without refraction and one with refraction, and then compute the optical flow. In this case, the refraction caused by the glass jar is so strong that the background is actually blurred out. So a reliable optical flow computation is impossible in this case, and color coding of these vectors fails. So this doesn't work. It's a failure case of background-oriented Schlieren. At the same time, the cameras always need to be focused on the background, which places the actual object of interest out of focus. So that's unfortunate. Our method works very reliably for out-of-focus situations, but also for in-focus settings, which is due to the smooth color coding in the light field, which I mentioned earlier. We've got some limitations that are mostly imposed by the prototypes that we're using. So the field of view of the lenslet arrays is limited. If the refraction is too strong, you get the repetitive effect that you get with all lenslet-based 3D displays, and you can see that in the photograph on top. So the refraction on the outside of the glass is too strong, and the data in that case becomes useless. The resolution is limited by the lenslets at this stage. If we had higher resolution probes or lenslet arrays, the resolution would be limited by the printing process actually, and we also have, well, I mean, the fidelity is limited by the color nonlinearities of the printing process. So you don't get the colors that you specify in a digital image when you actually print them on a transparency. There's also some color crosstalk that limits the performance. We assume that there's no absorption for most of the experiments, scattering, or emission within the refractive medium, and then the refraction is actually wavelength independent. So in summary, we've presented a new approach to Schlieren photography using light field probes or illumination, and which can present a portable alternative to existing technologies. We've shown that it works very well for refractive solids and fluids, The resolution limits at this stage make capturing gases challenging. We've also shown that we can encode a variety of different spatial angular filters in these probes. In the future, we'd like to focus on the reconstruction of refractive objects, and evaluate that a little bit more. And we'd also like to improve the performance of our prototypes, for instance, using holograms. So holograms could overcome the spatial angular resolution trade-offs, and you can actually order higher spatial angular digital holograms online on a website that I've listed here. So these look quite impressive, and we'd like to use those as probes as well. We'd like to test more sophisticated encoding schemes and also use our probes for different applications. So thanks for your attention, and happy to answer any questions.
Any questions? Yeah, I had a question. So you are proposing to use holograms instead of your LensLEC and color filters to create the structure?
Exactly. So holograms just allow you to specify intensity or color value, spatially varying and also directionally varying.
So would it be a volume hologram, I take it?
Possibly. I mean, I'm not entirely sure how the technology works for this company, but I believe that's what it is. But I'm not an expert on holography. We should probably ask Rob, who gave the last talk. You know, we'd like to experiment with this, but we haven't actually looked into it at this stage.
What limits the spatial resolution of this technique? The size of the microlens that you're using for the background?
Yes, so the spatial resolution is limited by the size of the lenslet array, and we actually have a table of all the different lenslet sheets that we've used in all the experiments in the paper, so you can look that up. The spatial resolution is, I can't give you a specific number, but it's decent, but not great. At this stage, we are more interested in the angular resolution, actually, because most of the filters that we've used are angular-only filters, and we've only used the spatial encoding for very few of the experiments.
And if you had like a gradient index element that you would like to measure, what do you think, what would be the minimum delta M that you could measure with this?
In the space?
Yeah.
Well, that depends on the probe. We used relatively large lenslets, just because we use off-the-shelf inkjet printers to print the transparencies. If you look at some of the 3D postcards, the lenslet size gets actually very small. But that requires digital offset printers and all that. For us right now, it's a 3 millimeter, actually, the spatial resolution. So it's not great.
Does the resolution change based on the refractive index? So like you showed a close-up of like the glass.
Right.
And then the image of the lenslet through the glass gets smaller around the edges of the glass.
Right.
Does that mean your resolution increases around?
Well, there is magnification going on due to the refraction, which is why background-oriented Schlieren failed in the case that I showed. So you don't actually get a lookup table, a direct lookup table of a, say, ray in a camera on the light field. It's actually an integration. It's a little bit more complicated. And if you use smooth encoding of the background light field, even the integration will give you the mean of that smooth color distribution or intensity distribution, which does limit the resolution somewhat, but yes, so yes.
But the image of the size of the lenslet is changing, right? Based on how much refraction it has.
Yeah.
Right? So you're sort of getting more resolution around the more refraction that you have away from the...
Well, you're integrating over a region on the background in space and angle now, right? So I don't think the resolution gets actually higher. I would say it gets lower, but it looks smoother. It looks like the resolution gets bigger, but that's only because you remove the intensity aberrations around the lenslets, actually. So it looks like it's better, but if you had a better encoding scheme that's not limited by the actual lenslets, I would say it gets worse, actually.
Thank you very much. That was a very interesting session. I would just like to add a few observations or comments. I think in some sense, even though all three talks were completely different, they had a common theme tying them together. And in the first talk, the gigapixels The reason why the geometric aberrations start coming in is your basic assumption of shift invariance that comes from the paraxial approximation. That starts breaking down as you go to wider and wider angles. So in the second talk and subsequent talks, whether you're talking about phase-space representations, Wigner distributions, or light fields, they are talking about non-stationary signals. In signal processing, the time frequency analysis was invented to handle signals whose statistical behavior did not stay stationary over time. So whether you are talking about shift variance that comes from violating the paraxial approximation, or whether you are talking about phenomena that are inherently non-stationary, you have to go to higher dimensional representations. So it would be interesting as we go further forward to see how the light field techniques, what implication they have in designing the wide angle, high resolution, gigapixel type of cameras. And just a higher dimensional representation, that is the phase space. And in the last case, the background, the standard background-oriented Schlieren photography, you just had a two-dimensional structure. Instead, by adding lenslets, you added a few more dimensions, and therefore you got the powerful results that you did. So on that note, I want to thank all the speakers for excellent talks, and all of you for very interactive and interesting questions. So now we are breaking. So Srinath,
10 minutes.
10-minute
We are
break.
over by about 7 minutes.